Hello friends, here is the first video. So keeping in mind that the first term exam of class 12 students are approaching fast, I will be starting with the topics of class 12 until December. And today I will focus on the problems of electromagnetism. And here is the first problem. A thin circular ring of radius r carries a uniform surface charge density sigma. Calculate electric potential and field at the axis of the ring. So what is being told is that here is a circular ring of radius r whose thickness is negligible in comparison to the radius. Its surface charge density is uniform. We will assume that its thickness is delta r. Calculate electric potential and field at the axis of the ring. So this is the axis of the ring. Now we have to calculate electric potential and field at this axis. So the charge here is del q. Assume a charge dq here and find the potential due to this charge at the point P on the axis of the ring. Suppose this distance is r. Now this distance is constant, radius of the wire, and this distance, assuming Cartesian coordinate systems, this is the z-axis and the ring is lying on the xy plane. So sorry, this I should have told earlier where the ring is placed. Still, this is the origin. So the potential due to this elementary charge dq at the point P will be d phi equals to dq by 4 pi epsilon naught r. Now integrating over the whole ring, you will see that this r is constant, so it will come out of integration. Only thing that will be integrated is dq, which is equals to the total charge of the ring. So potential phi will be equals to 4 pi epsilon naught r. But what is q? I have assumed that q is the total charge of the ring. How to find out the total charge of the ring? So for that we need we have to multiply the area of the ring with sigma. Now by the term area I means the area of the strip. If the ring, imagine that the ring were to be opened and made flat. So what would happen is that it would be resulting in a strip having the thickness delta r here, and the length will be 2 pi r, and its charge density is sigma. So q will be equals to sigma 2 pi r into delta r divided by 4 pi epsilon naught. Let's write it into the terms of r. It will be epsilon naught r square plus z square root over this phi. Now this is the electric potential. So we have solved half of the problem. Now we have to find the field at the axis of the ring. So this can be found out very easily. I know that many of you were thinking that there is an easy process to find out the field at P, that is by using integration, but that process is very much common and you will find it in all textbooks, so I am not going through it here. So it is in concept, so I am using a different ink for it. It is an important formula that E is equals to minus grad phi. So grad is an operator that we will learn in your higher classes, but nowadays most of the books have it. books of class 12 have this thing. This can be just written as minus of del x del phi by del x plus del phi by del y plus del phi by del z. Here phi is a scalar and this is an operator known as grad operator. E is known as the gradient of phi. Phi will get this because the curl of electric field, leave that, no need, you may get confused. So the short thing, the concept here is that electric field is the gradient, negative gradient of the potential. So here is this, and now as you can see here, r is constant, only z is variable. So when you will differentiate with respect to x, so del here represents partial differentiation. Partial differentiation. When you differentiate, del x represent, you will del x not equals to so this is total differential and this is partial differential. When you will use del by del x, you will differentiate only with respect to x, and so on. Here you will treat y and z as constant, and so on. Here the only variable is z, so you will just use del phi by del z because the rest of the differentials will be 0 here. So electric field, this minus sign is due to the factor. So first I will take out its magnitude, then for that I need to do its grad as it is. What is it? Then sigma 2 pi r delta r 4 pi epsilon naught. Now r square plus z square, a bit of mathematics here for those students who do not have maths in their class 12. So this has the same formula as the formula for total differentiation. So this is something like ddx of x square plus a square 1 by 2 minus 1 by 2. Now do this, whatever you will get, that is the formula. Okay, let me do it for you. Plus to minus half plus minus 1 will be added here, so minus it will be minus 3 by 2. It will go, I am taking it to down, a square 3 by 2, and I will differentiate the inside one, chain rule, simple. So x by x square plus a square to the power 3 by 2. Done. So here instead of x it should be z, and instead of a it should be r. So let me substitute it here. Electric field will be sigma by 4 pi epsilon naught x square plus a square to the power 3 by 2 z square plus r square to the power 3 by 2 into z. In board's exam, okay, now it is MCQ, you don't need to show it, but still in the rough work, try to do it in terms of z. Don't be in the comfort zone that every different derivative you will do in terms of x, as it is written in most of the formula book of mathematics. So this is the electric field. And one more thing, here should be a minus. Since there was a minus outside, it is already getting nullified by it, so I can write it in the terms of E vector, where E vector is a function of Z vector. That's all. You can further simplify it. Okay, now let's quickly go to the second part of the problem. I am explaining more, that's why it is taking 10 minutes. Otherwise, if you see, this solution is very much small, pretty small, and if you practice it once by yourself, it will take you just 1 minute to do the whole problem. So let's go to B problem. So it is not visible from here, I am explaining it pictorially. Okay, so this problem says that a large circular ring, okay, the ring is circular. I am placing the ring on the xy plane and placing my z-axis here. Z is upside. Okay, so x should be on the front side and y on the right side. This is okay. Right-handed coordinate system. An electron of mass m. This is a large circular ring. Whatever information, radius is r. Okay, radius is also r in this ring. So okay, and charge is q. So in the earlier problem, I was given a uniformly distributed charge density. In this problem, I am given a uniformly distributed charge, which is written as q. So workload reduced. I have to find the angular frequency of oscillation of electron which is placed along the axis of the ring. So here is an electron placed in the axis of the ring. Okay, so at first note that it is an electron, therefore it will experience attractive forces. It will be attracted towards the ring. As you can see in the previous problem is for a positive discharge. So a positive charge will face a force. Will be exerted upon by force that is in the z direction. That is in the z-axis, z cap direction, or along the z-axis, or away from the ring. But since it is an electron, it will be exerted upon by a force towards the ring. So what will happen? Let me show you the scenario. Once it will be attracted at the center of the ring, at the center of the ring, a force will be there or not, that we have to see. Okay, let's see what will happen here. As it is very clear, at the center of the ring, Z will be 0. So electric field will be 0 at the center of the ring. So no force on the ring. But since it has been acted upon by such a large force, so it is a case of SHM, as you can see. Like in the case of a simple pendulum, this position is when the electron, when the bob is as its maximum amplitude, and the center of the ring, you can approximate it with the case when the bob momentarily comes to its mean position. At that point, it has maximum velocity. That's why it goes to the other position, which is a point of unstable equilibrium. That's why it comes back and goes on. So the electron will come here. Again, it will reach some point. Again, it will go there. There is an additional theory. Okay, let me give you an exercise. So this is the electric field. You can differentiate it and plot a graph along the axis of the ring. Plot a graph of electric field along the axis of the ring. You can do it by differentiating it and finding out the maxima and minima. It will be a pretty interesting exercise for you. After plotting it, after doing that, you can plot the graph, and then you can easily find which is the point of stable and unstable equilibrium. Okay, so let's do it. An electron of mass m charge E oscillates the ring See, while solving the problem, even though I'm explaining it to you, I'm reading the question many times, such as this question I have read 2 to 3 times. So this habit you should inculcate in yourself, that you read the problems a lot, so that no information get missed and your interpretation gets better. Okay, so quickly let me write the expression for the electric field. Electric field will be first. Tell me what is the potential at this point of the ring. Say it is P point. So the potential will be Q by 4 pi epsilon naught R. Okay, and electric field same, right? Only thing is that whatever long expression I have written in the earlier case, sigma 2 pi r del r, that you have to replace by q. That's it. So directly you can write q z. I'm not writing it in the form of vectors. Okay. So so not z square plus r square 3 by 2. So the force that the electron will be experiencing I am not including the minus charge here, because if I would have written in the form of vector, like a vector, e vector, I should have written minus to imply that to imply the opposite direction. E q z 4 pi epsilon naught z square plus r square 3 by 2. Now comparing it with the form of f equals to, okay, let me write. Okay, now in a harmonic oscillator or a spring block system, you must have encountered with this equation f equals to minus kx. It is the equation of restoring force, and you will find it at the first page of HC Verma's book in the chapter of SHM as well. So comparing with this equation, both are for restoring forces, you get this to be your k, this to be your distance from the center of the ring. So it comes out that k is equals to eq. Okay, I am writing it to be r. R is equals to z square plus r square to the power 1 by 2 q by 4 pi epsilon naught r cube. It is the value of k. Now there is a formula, omega, or the angular frequency, is equals to root over k by m, or k equals to m omega square. So using this, eq by 4 pi epsilon naught m r cube, not square. So this is the value of angular frequency. So we have solved both of these problems. Let's proceed further. This is the last problem of today's class. So we have to find out the correct representation of electric field lines of force. So as you can see here, I have not explicitly mentioned the charge. In boards you can get a question that whether it is positive or negative charge. That's definitely a positive charge, and you have to find out the correct representation. So let's figure out the options. So in option A, everything looks pretty correct. The only thing is that this field of line of force is correct. It has emanated from the conductor at an angle of 90 degree, but this field of line is not 90 degree. Only for this field lines the entire option is wrong or eliminated. In this one it is not 90 degree, this one is not 90 degree. In this one it has pervaded the conductor, which is false. Only in this problem we can find all the things roughly equals to 90 degree. Which is not found here. Even at the inner part of the at the hollow part of the conductor, which is not found here. So this is the correct option. Okay, so I'm done for today, and also I would like to suggest some things from the HC Verma source book, chapter 1, electric field. Sorry, it's chapter number 29. So the previous problem I have solved using by finding the potential. You can find this alternative method in example 29.2 of this book. More about electric field lines of force you can find in the section 29.4, and more on partial differentiation you can find in page number 110. And this problem was related to equipotential surfaces. I have not covered today in that much extent. You can find all the proofs in the further chapter. For today, in the chapter of electric field and potential, there is a small section. You can read that. Also, you can go through some of the PYQs of the chapter corresponding to this book. I have referred the name of the book. Once again, I am referring to it. Or let me show it to you. It is this book, IITJEE Physics. So this book I am following. So here you can find many problems related to that. Okay, that's it for today's class. See you then.